We'd like to use this video to model some reading strategies that are useful when reading the types of dense information that's found in science textbooks. The trick is identifying what is important in a chapter or in a paragraph, and then making coherent written or typed notes. So some of the strategies that we might use are read and write or summarize. Rereading is not effective. It's actually the writing process that embeds a lot of this information in your brain. We're going to start with some energy concepts from Chapter 13 in Smith's Exploring Chemistry. So there's two definitions that are in the first page. The first was work, which is the work done for the amount of force exerted over a distance. And the second concept is energy, which is the capacity to do work. Both of these are measured in joules. Energy is really the potential to do work. In chemistry, we often use energy. There are about 7 different types of energy. There's mechanical, heat, chemical, electrical, light, sound, and nuclear. In chemistry, we use mostly heat and chemical energy, although for electrochemistry we would use electrical energy, and for photochemistry we would use light. Mechanical energy, it must be noted, is both kinetic energy and potential energy. So that kinetic energy is the movement due to molecules which are whizzing around, whereas potential energy is the energy that's contained within their bonds. The next piece of information that is extremely important from this chapter is the conservation of energy principle. Energy is always conserved. Because of this, energy is neither created nor destroyed, but can be changed from one form to another. So chemical energy can turn into electrical energy, mechanical energy can turn into heat energy. The examples are given in the figures in the chapter, which show the conversion of energy between various forms. Remember, they're neither created nor destroyed. However, most conversions are not 100% efficient, and so heat energy is often given out as waste, as shown in all of the diagrams in figure 13.2. And they're classed as Sankey diagrams. The second concept that was very important in this chapter is the concept of heat versus temperature. I have 2 definitions here. One is that heat is the measure of total kinetic energy, and that temperature is the measure of the average kinetic energy. When we're talking about temperature, we're talking about hot and cold, and it's measured in degrees centigrade, degrees Fahrenheit, and also in Kelvin. The total kinetic energy of all the molecules, remember, is the kinetic energy of the movement of molecules, but also the vibrational, rotational, and translational movement within the molecule. Sometimes it's called internal energy. And when we measure heat, we generally measure a change in energy. Heat always flows from hot to cold, so from a hot temperature to a cold temperature, until thermal equilibrium is reached. This is the second law of thermodynamics. So, how do we measure the amount of heat? Well, we know that it's proportional to the mass, and it's also proportional to the nature of the material. So, hot water has less energy than hot oil. This dependence on the type of material is called Zipf and is measured in joules per Kelvin per gram. And there's a nice little definition which I'm just going to cut and paste to put into my notes. So the specific heat capacity is the amount of heat that's required to raise the temperature of 1 gram of the substance by 1 degree. In physics, we often talk about it in terms of kilograms. Water in chemistry is 4.18 joules per Kelvin per gram. In physics, this same substance would be measured in kilograms, which is the SI unit, and that would be 4,180 joules per Kelvin per kilo. There's also a concept called molar heat capacity. Often we might not want to have to convert things into the mass, so we can use the molar heat capacity. And again, there's a definition which is just cut and paste from the textbook, which defines this variable. And that's measured in joules per Kelvin per mole. Given these specific heat capacities and molar heat capacities, we can come up with a relationship between the amount of heat and the amount of temperature change that it undergoes. Well, this formula is called delta Q is equal to M times the specific heat capacity times the change in temperature, where the change in temperature is always the final temperature minus the initial temperature. We will go through some worked examples in class. Because of conservation of energy, the amount of heat that is gained is equivalent to the amount of heat that is lost in a material. And this is assuming an isolated system where there's no heat loss to the environment. I tend to use heat loss as a negative substance. And this is because the change in temperature, T final minus T initial, is negative. Alternatively, you can think about it as the sum of the heat. So the change in heat is zero, which is another expression of the conservation of energy law. The last concept in the chapter was latent heat, which is hidden energy. And this is basically when there is no temperature change at all. The best way is to watch the videos that are posted on the Schoology site, which give a very good example of no temperature change when it goes through this latent heat transition. And the key is that it's a phase transition, so it's a change of state. Table 13.2 can be drawn up actually as a triangle, a diagram, which looks at the change of state between a solid and a liquid, which is called melting, between a liquid and a gas, which is evaporation, and between a solid and a gas, which is sublimation. The reverse process is condensation from a gas to a solid, also condensation from a gas to a liquid, and from a liquid to a solid, freezing or solidifying. Now, it's not expressly written in the chapter, but a simple way of thinking about this change of state or this change in energy is to consider it as a change in heat. So you're looking at the change in heat energy for fusion, which is the mass times the latent heat of fusion, or the change in energy for vaporization, so the vaporization energy, which is the mass times the latent heat of vaporization. This latent heat of fusion is basically the heat that is absorbed or released during a change in state. So it would be absorbed to go from a solid to a liquid, and it would be released when it goes from a liquid to a solid. I find the easiest way to think about latent heat changes is to use a graph. If you indicate the temperature on the y-axis and time on the x-axis, you can consider the time as the change in energy that's supplied. And you can look at a phase transition or a heating curve or the reverse, which is a cooling curve, and identify each of the states and each of the changes in states. At the lowest point of the curve, it would be a solid. In the middle, a liquid. And at the top, it's a gas. The intermediate flat regions are where there is no temperature change, so no change in that y-axis, and that's due to the latent heat of fusion and the latent heat of vaporization. And at these points, it's a change in state, but there is also some solid and some liquid, or some liquid and some gas, so both of these particles exist at the equilibrium. The latent heat of vaporization can be in joules per mole or joules per gram. If we do it in joules per mole, then we use the formula delta Q is equal to N, the number of moles, times the latent heat of vaporization. Delta Q is the mass times the latent heat of vaporization. Which one you use depends on which one you're given in your table or in your question. A good problem-solving strategy with these latent heat questions is to always sketch a graph. If you consider the time axis as a representation of the energy change, then each of those sections of the graph is a change in energy. And so your total energy is the sum of the energy of the solid, heating from a low temperature to a medium-sized temperature, say T1, and the change in state from a solid to a liquid, so delta QF. Then also the change in energy from that melting point through to the vaporization point, which would be delta Q2, plus the change in energy due to the latent heat of vaporization. And finally, up to the final temperature of the gas. So Q1, Q2, and Q3, plus the change in state, so QF and delta QV. And you must include those phase changes. Even though there's no temperature change, there is a change in energy. Writing out that total equation is much simpler now. And once you've identified each of the temperatures on your graph, you can plug it into your equation. And it's a very simple way of solving these rather complex problems. One thing to note is that the specific heat capacity is different for different phases. So the specific heat capacity in the first temperature change is the heat capacity of the solid. In the second temperature change, it's the specific heat capacity of the liquid, which is different again. And finally, you use the specific heat capacity of the gas. The last point in the chapter was something that is probably from your Year 11 chemistry course. Only a pure element has a heating and cooling graph such as that's sketched. A compound would show many more phase changes and that's one way that you can distinguish pure elements from compounds. The other thing to note is that even though I've structured this as a linear graph, linear sections, it is actually a heating and cooling curve, and it does follow an exponential curve if it's a cooling curve. And heating, it's very hard to get it to heat at a uniform rate, and so very often it's not linear.